So does anybody remember what happened here 3 weeks ago?
How much time do I have? How much time do I have?
Yeah,
3 weeks ago, you weren't here. 2 weeks
two.
ago.
2 weeks ago, I wasn't here. I distinctly remember that.
No.
3 weeks ago.
1 week ago, you weren't here.
Oh, I'm sorry, 2 weeks, so 3 weeks total. So 2 weeks ago, what happened? This math guy, I tell you what.
You reviewed a lot, talked about the rotor.
Because there was nothing there.
We couldn't
Yeah,
get
that's right.
that to work, right? So we had a bug in the system. Then 1 week ago, I had a bug in the system. Now, some of you don't recall this, but they used to have this malady called the flu. And then with the advent of the big C, the flu disappeared, didn't it? Because according to CDC last year, how many cases of flu were there nationwide? But again, math guy, 0, right? Well, I was one of those statistics last week. Okay, this week, what don't we have? Internet. I quit. Except yes. So I love to get to college. I use these a lot. I never use PowerPoint because the students were all used to PowerPoint. And I get up with these and they think, whoa, this is new. Seriously, so they loved it. So we do have the slides, but there's a whole bunch of embedded videos that I can't show you. And so we'll just, and so then I get here and this wouldn't talk to that because the battery died in the week that I didn't use
Are
it.
you sure it's in right? Because I think I dropped that and I think I might have put it in backwards. Sorry, I just realized that during the week.
Jezebel speaketh. Okay.
Oh, check it. I don't know.
Well, I think the pastor already threw that one away, but okay.
Well, then he put it right. Sorry.
I can only use phrases like that because this isn't being recorded, right? But anyhow, so.
It actually is.
Uh-oh. My dear wife, Jezebel, how's that? Okay, so let's see what we got here. So anything with a video we can't look at. So I will come back and we'll show you eventually all of these videos, okay? So here's the basic structure. Did you guys see this? Yes, sir.
I think you got a Wi-Fi.
No.
I think so. I think you're.
Well, we'll try it here. Did you guys see this video?
No, we haven't seen that one.
Okay. So son of a gun, let's do this.
Is that the ball thing?
No.
Many species of bacteria propel themselves through their environment by spinning helical motorized flagella. Rotobacter cells have one flagellum each, whereas E. coli cells have multiple flagella that rotate in bundles. Each flagellum consists of a helical filament that is 20 nanometers wide and up to 15 microns long, and spins on the order of 100 times per second. These animations show a series of schematized and speculative models about how bacterial flagella might function and assemble. Just outside of the cell wall, the filament is connected to a flexible rotating hook. The filament, the hook, and a structure called the basal body, located below the cell surface, make up the 3 parts of the flagella.
There's the cell
The
membrane.
basal body consists of a rod and a series of rings embedded in the inner membrane, the peptidoglycan layer, and the outer membrane. Some of the rings make up the flagellar motor, which can be divided into 2 major parts: the stator, which is attached to the peptidoglycan layer, and as its name implies, remains stationary, and the rotor, which rotates. The motor derives its power from a proton gradient across the membrane. In this example, a high concentration of protons exists outside, and a low concentration exists inside the cell. The protons flow through the interface between 2 types of proteins, called mode A and mode B, that make up the stator. Mutational studies suggest that a conserved aspartic acid in mode B functions in proton conductance. Each stator contains 2 mode B proteins, and therefore also contains 2 of these important aspartic acids. Although the molecular mechanism of rotation is not known, one possible model describes protons moving through the channels in the stators and binding to the aspartic acid in the mode B proteins. This binding causes a conformational change in mode A proteins, resulting in the first power stroke that moves the rotor incrementally. At the end of the first power stroke, the 2 protons are released into the cytoplasm. The proton loss causes a second conformational change that drives the second power stroke, once again engaging the rotor. Although the mechanism for motor function is not yet certain, many details of flagellar assembly have been determined. Flagella begin their assembly with structures in the inner membrane. 26 subunits of an integral membrane protein called FLEF come together in the plasma membrane to form the MS ring. The FLE-G proteins assemble under the MS ring. FLE-G, along with FLE-M and FLE-N proteins, make up the rotor. Flagellar proteins destined to be part of the extracellular portion of the flagellum are exported from the cell by a flagellum-specific export pathway and assembled at the center. Mode A and Mode B form the stationary part of the flagellar motor, the stator. Both are integral membrane proteins, but Mode B is also anchored to the rigid peptidoglycan layer, keeping the stator proteins fixed in place. The subunits of the rod portion of the rotor move up through the hollow cylinder in the assembly, and assisted by cap proteins, build up the rod in a proximal to distal fashion. Another set of rings, called L and P rings, are found in gram-negative bacteria such as E. coli. They penetrate the outer membrane, forming a bearing for the rod. As the rod cap is exposed outside the L ring, it dissociates and is replaced by a hook cap that guides the assembly of the hook proteins. After the hook is assembled, the hook cap dissociates, and a series of junction proteins assemble between the hook and future filaments. Finally, yet another cap is built, and filament proteins assemble. Like the rod and hook proteins, they travel through the hollow channel inside the filament to reach the distal end. The cap rotates, which causes the subunits to build in a helical fashion. A complete filament can consist of 20,000 to 30,000 subunits.
Do you get all that? So we'll talk briefly about that. Let me go back to this guy. So again, what we were looking at here is you have the inner and outer cell membrane. How thick is that cell membrane on the outside? Well, how many cells, how big is a cell? 120 to 125th of a human hair. The cell membrane, so again, this would be a big circle here, right? And then the goo of the cell is down here. So there's your cell membrane, which is a few millionths of an inch thick. Coming out of that is this flagellum that they just talked about. So when they were talking about the mode A and the mode B proteins, and they undergo a conformational change, just the shifting of those protons, think electrons, the reverse of electrons, causes those proteins to undergo a slight shape change. So just the movement of those two proteins change shape, and that causes this rotor to turn just a little bit. As soon as it turns a little bit, it loses those protons. They stop the shape change. which then causes 2 more protons per protein to get pumped in, and it does that, every time it does that little thing, it causes the rotor to turn inside the stator. And we said in some flagellum, they can get speeds of over 100,000 revolutions per minute, stopping within a quarter of a turn and reverse switches. So over the past few weeks, I've seen a lot of that old guy in the back row there, because he likes to work with, yeah, you, Dave. He's doing a lot of machine setup for rotary airlock, and I don't do the high-tech stuff, I've just been helping clean. So it's been fun to watch Dave from a distance. He just kind of gets in it. Some of these machines are fairly simple, some are much bigger, and he'll go in and, you know, after they get them leveled, he goes in and he's measuring and checking the run and the traverse and all the other stuff that he's doing. But as complex as his machines look, they basically have a spindle, most of them do, right? And they'll have a bed on which parts can move back and forth, and they've got a motor, so parts can move back and forth. Some cases they can move this way, and then the spindle can move up and down, and they've got a cutting head. Without making it excessively simplistic, the machines that, at least the non-computerized machines that Dave is working on, have a basic few parts. Do you get that? And yet, nobody is going to look at, like even a drill press, and say it evolved by chance. How complex is this compared to a simple drill press? Infinitely more. And yet, they will absolutely draw the line in the sand and say this happened by chance. Time and chance. Time and chance. So any questions on this? This is
So the
what
flagellum is in what cells again?
sperm. In humans, it's sperm.
It's just, that's the only thing.
In humans. Otherwise, it's in bacteria. Yeah, bacteria have it. Yeah. And they'll have 1, 2, or 3 depending. And these buggers book, right? They'll zip along at speeds of about 60 to 200 miles per hour if they were 6 feet big. Okay, now there's a Hollywood B movie that would be interesting to watch, The Attack of the Flagellum or whatever. Okay, let me make sure we're cooking on this thing from the current slide. Okay. We've done that. We've done that. Okay. Now, onward and forward. And if you run out of information, let me know, because I've got 2 more sheets up here. Good? So you should go up through 74, and then I'll have to get you additional items. So, excuse me, please, as we go forward, if you have questions. So, one other thing to give you a perspective, that little tube that comes out, that flagellum, it's a hollow tube. How big in diameter is that? 20 nanometers, which is 20 billionths of an inch thick. And all the little subunits that make it up, all self-assembled within 20 minutes. Okay, so let's talk about reproduction. I'm glad to see we have no underage people here, so it's safe to talk about this. So there's 2 problems with reproduction, at least that I can think of right off the bat. Problem number 1, is a baby part of the mother's body? No. As cute as those little buggers might appear, they are foreign parasites. Do you catch that? You were a foreign parasite before you were born. How's that perspective? Okay. A parasite, and now we're talking biological terms. A parasite derives all its nutrition from the host, correct? So it makes babies are parasites. And then they get born, or are they still parasites? Oh, that's a philosophical question. We'll save that for later. But it's foreign in that its DNA is separate and distinct from the mom's. Do you get that? So a baby is biologically and immunologically entirely separate from the mom. That's the first thing. So somehow this little developing thing has got to be protected from mom's immune system. Or mom's immune system will do what? Kill it. Got it? So when gals say, I have control over my own body, well, you have control over your own body before you get pregnant, but once you get pregnant, that little thing is not part of your body. So that is a fallacious argument, immunologically, that people use. So that sounds bold and strong, but that's the case. Secondly, you already know egg plus sperm equals zygote, right? The new little bugger, the little tax deduction. Chromosomes. Most of the cells in your body have 46 molecules of chromosomes, or DNA, per cell. Then what they'll do is before pregnancy occurs, you develop, of course, eggs and sperm. Eggs have 23, sperm have 23, so we'll depend on the math guy here now. 23 plus 23 equals 46. So most of your cells are 46. Ladies, eggs, 23, men, sperm, 23. That's how you undergo what's known as meiosis 1 and meiosis 2 to get from 46 to 23 for the eggs and sperm. You got the math? Okay. So here comes the sperm, here's the egg, and now obviously on this little race for pregnancy, is the guy typically releasing more than one sperm? Oh yeah, like hundreds of millions of them. And most people get this wrong, so that's okay. If you have more than one sperm getting inside an egg, what is the problem?
Is that Down syndrome?
No, that would be trisomy 21, just on the 21st. Most people say you have twins. Well, no. If you have, let's say, 2 sperm actually get inside an egg, what's the math? 69. And if you don't have 46, you don't have life. Do you get it? So the first problem is, how do you protect the new little tax deduction? The second problem, how do you design it, there's that word, how do you design it so that 99.99% of the time, conception will be 23 plus 23? Because if a second sperm got in, you would have nothing. Do you get that? That's 2 huge issues. Keep that in mind, please. So here we go, folks. Egg plus sperm, and then you have this structure called the zygote. So we can look at this nice little deal. So here, of course, we have the uterus, and eventually what's going to happen, that egg plus sperm equals the zygote, is going to implant on that uterine wall, and as it does, it will begin to burrow in. There's 3 layers to this. You have the inner endometrium, and then you have the thick muscular myometrium, and as this burrows in, essentially what's going to happen is the mom end of thing, the endometrium, will eventually develop blood vessels. So if we do it from a perspective here comes our little zygote guy. As he burrows in, he is going to eventually develop blood vessels going this way. Mom's going to develop blood vessels this way. Can they exchange blood? Because if they exchange blood, it would be like getting the wrong transfusion. If you get the wrong transfusion, does anybody know that big word? Agglutination. And significant agglutination, it's kind of like clotting, it's not the same, but it's kind of like clotting, and that will result in death. Do you get it? So little goober's eventual blood supply cannot intermix with mom's developing blood supply, or you will lose goober every time. Now, I felicitously say that everybody's up on the mantle of their thing. They have a picture of goober, right? All the little tax deductions that they're blessed with. But what was that organ after the delivery that gets pushed out from the uterine lining and ends up in the trash? If you guys had any idea of the magnificence of that structure, you would take a picture of it and put it up on the mantle with everything else. I mean, it is just... and you're saying you're nuts. I know I'm nuts, but seriously, you get a feeling for all of this and you think, it is incredible, folks. So here we go. So, ovulation, here's the good old ovary. And I'm not even going to get into all the stages of that. We don't need to, and it put me asleep. But here comes that little egg called the oocyte, right? And as the oocyte, so you've got, so here's the uterus, and here's the two fallopian tubes. You got it? Okay. So you got the left and the right. And by the way, for the normal female, 1 month, the left ovaries doing the ovulation, right? The next month, so your ovaries, ladies, are on vacation half the time. Unless you have to have one removed, then what happens? If one gets removed, the other one doesn't get a break anymore. It automatically picks up the slack. Okay, so you got it? Here's an ovary here. There would be another ovary here. Left, right, back and forth they go. They get picked up in these fallopian tubes, and these guys are lined with cilia, those little hairs. And those little hairs will go ahead and help swoosh the eggs, not eggs, technically the oocytes that way. In the meantime, under certain appropriate circumstances, which we're just going to assume that you guys know what take place, in comes this rush of the knights on white horses, right? So in they come, and they kind of go, they have no traffic signals, they just come roaring in, some go left, some go right, typical of most guys, they get lost, but that's okay, there's plenty of them. Okay. So those little dudes with their outboard motors, you know, they're zooming this way, and our little egg friend, oocyte, is going this way. Most fertilization, which we're going to talk about in somewhat detail, is phenomenal, that occurs in the lateral third. So either over here or over here. Got the picture of stuff? Okay. Fertilization occurs. So here's our little dudes, the sperm, okay? So then, with fertilization, what will happen? 1 + 1 = 1. Takes a real man to say that. Good. Okay, egg plus sperm equals a zygote, right? Which is a single cell. Over a period of time, then that baby will split, and it goes to 4. It turns into another thing called a morula. Then it turns into another thing called a blastocyst. Now, the interesting thing is, eggs are real big and sperm are really tiny. The reason an egg is, they both have how many chromosomes? 23. Oh, you guys are sharp. The reason the egg is so big is because it has to contain a lot of food. Okay? So, and then I used to say this all the time at school, and then I got saying it less and less because I didn't want anybody to kill me. So, do the sperm have the ability to move around? Yeah, because they got the flagellum, right? And so, to the conception party, what do the sperm bring? DNA, and they drive. What do the eggs bring to the party? DNA and food. So, you're figuring out where a woman's place is, and no, we're not gonna. I tell you, I'd get some eyes rolling, but By then they realized I was nuts. So we get over this blastocyst. Now, the only difference between, and these are not the size, the difference between this and this is this. They are getting no nutritional support yet. Single cell, it divides, it begins to hollow out into basically like a soccer ball with an outer layer of cells and an inner layer of cells. Those inner layer of cells are called embryonic stem cells. You heard that term before? Embryonic stem cells. You're made up of about 246 different kinds of cells. All of these inner layer of cells in there have the ability genetically to turn into any of the 246 different kinds of cells that you possess. Within a week or two, as this thing turns into an embryo, these inner embryonic stem cells become known as adult stem cells, and their ability to differentiate or change is limited. I know that's confusing, but you get the idea. So it's showing you this, and then finally right here, this blastocyst, this soccer ball, double layered, it begins to implant into the uterine lining, known as the endometrium. Good. Okay, continuing. Now, day 5 or 6. So right here, this is the endometrial lining of the uterus. You can see how it's looking. You can see this is the uterine lining. This represents the capillaries, so it shows you the vascularity. And you see over a period of a few days, literally within 2 weeks, you see how you're getting more and more capillaries in here, so much more blood supply. And this little dude, and how it attaches is beyond what we want to talk about here. But do you see it's beginning to develop these roots, so to speak, and burrow in here? So by day about 8 or 9 after fertilization, it already is well attached. So for a number of years, I think, are you 486? Is that it, Deborah? The morning after pill? Okay. For years and years and years, it was resisted in the United States. Finally, circa 2000 plus or minus, it was approved in the United States. And do you know what that RU486 morning after pill does? It causes such violent contractions of the endometrial lining that it will either dislodge this thing that's already firmly attached, or if it's down in here, it will actually crush it. That was the morning after pill to get rid of what? Unnecessary stuff. And I remember a number of years ago, the head of the American Gynecological Association said any house in the United States that has a female age 12 or older should have RU486 in the medicine cabinet. Pretty tough to take. So, implantation. Questions before we hit this? Do you kind of get what's going on here?
Implantation of the blastocyst usually occurs 6 to 8 days after fertilization. By the end of day 8, the blastocyst has burrowed into the endometrium of the uterus. At this time, it is composed of 2 main components: the outer cell mass, the trophoblast, and the inner cell mass, the embryoblast. As the trophoblast makes contact with the endometrium, it differentiates into 2 layers, an inner cytotrophoblast and an outer syncytiotrophoblast. The embryoblast differentiates into a bilaminar embryonic disc composed of two cell layers, the hypoblast and the epiblast. Soon after the embryonic disc has formed, a cavity begins to appear between the epiblast and the cytotrophoblast, known as the amniotic cavity. Cells originating from the hypoblast begin to migrate, forming a thin membrane, which covers the inner surface of the cytotrophoblast. This is called the exocoelomic membrane. The exocoelomic membrane and cells of the hypoblast together form the walls of the primitive yolk sac. By day 9, the blastocyst is completely embedded in the uterus wall. At this stage of development, the growth of the syncytiotrophoblast and cytotrophoblast is much quicker than the bilaminar embryonic disc. Small holes called lacunae begin to form in the syncytiotrophoblast as it continues to expand. By day 12, the lacunae stop growing and fuse to form large interconnecting spaces called lacunar networks. Capillaries in the endometrium surrounding the developing embryo dilate, forming maternal sinusoids. As the syncytiotrophoblast continues to expand, enzymes begin to erode the lining of the sinusoids and uterine glands, allowing maternal blood and uterine secretions to flow into the lacunar networks, establishing a uteroplacental circulation. The blood and uterine secretions only come into close proximity to the embryo, allowing the exchange of gases and metabolites. Around the same time, a new population of cells appear between the inner surface of the cytotrophoblast and the outer surface of the primitive yolk sac, known as the extraembryonic mesoderm. Large cavities begin to appear in the extraembryonic mesoderm. These gradually fuse to form one single cavity, called the chorionic cavity. Around 13 days after fertilization, a large portion of the exocoelomic cavity is pinched off, forming a smaller cavity, the secondary yolk sac. By the end of the second week of development, the chorionic cavity enlarges, and the bilaminar embryonic disc is joined to the trophoblast by a band of extraembryonic mesoderm called the connecting stalk, the future umbilical cord.
You kind of get that? Okay, so let me hit this and then we can have another video to follow up on that. So you saw what was taking place over here. Well, goober was developing, and every time they would use that word embryonic or something with embryo, you know that was the future goober, right? That was the cells that were going to actually develop. You had the chorionic, which is the protective layer, which also was going to develop the blood supply. So here's goober working his way, or I should say goober working this way, and mom developing eventually those blood vessels. Did you hear that big word, syncytiotrophoblast? Okay, so what you literally have, if you have these two sets developing, excuse me, of junior and developing of mom, those capillaries can never actually swap blood. Nutrients can diffuse across, but you have to have a barrier between there. So there is a group of cells, let me do it this way. There's a group of cells called the syncytiotrophoblasts. So as these guys are doing this, these syncytiotrophoblasts develop a 3D configuration of a single layer of cells so that the maternal and junior's blood supply can never cross. Because if it did, junior would die. Now this is what's interesting. Almost all the cells in your body reproduce and produce more cells. Once all these syncytiotrophoblasts have developed their protective barrier, they begin to coalesce In other words, this cell hooks up with this cell and they become a bigger cell. And then they kind of snarf up the other syncytiotrophoblasts, do you follow me? So that whole protective 3D layer eventually becomes one large cell called the syncytiotrophoblast. How did that happen? Time and
How big does that eventually get? Does that last all the way through the pregnancy then?
all the way through the pregnancy, yes. And eventually, I mean, it literally becomes, I can't give you the square inches, but based upon the size of the placenta, with all of those tiny, tiny little villi, right, with the blood, with the capillaries in there, the thing's gotta be several square feet.
So is that gonna be like the largest cell?
Yes, in that sense, it would become the largest cell, but it's the only one that coalesces as opposed to continues to divide.
Okay.
Just kind of like, I wonder how long it took God to think, how are we going to figure this one out? You know, it was just like, it's just crazy. It really is, folks. Excellent question.
Development of the placenta begins during implantation. When the blastocyst adheres to the endometrial epithelium, trophoblast cells differentiate into an inner cytotrophoblast layer and an outer syncytiotrophoblast layer. As the cytotrophoblast proliferates, newly formed cells migrate into the syncytiotrophoblast and lose their cell membranes, forming a rapidly growing multinucleated mass. The cytotrophoblast secretes proteolytic enzymes, and the syncytiotrophoblast sends out finger-like projections, allowing the blastocyst to embed into the endometrium. Lacunae, or spaces, begin to form within the syncytiotrophoblast. As the syncytiotrophoblast erodes the endometrial blood vessels and glands, the lacunae become filled with maternal blood and glandular secretions. Isolated lacunae fuse to form a network through which maternal blood flows, thus establishing early uteroplacental circulation. Toward the end of the second week, small projections of the cytotrophoblast begin to expand into the syncytiotrophoblast, forming primary chorionic villi. Early in the third week, extra embryonic mesoderm flows into this villi, forming a core of loose connective tissue, at which point the structure is known as secondary chorionic villi. By the end of the third week, embryonic blood vessels have begun to form in the extra embryonic mesoderm of the secondary chorionic villi, transforming them into tertiary chorionic villi. Cytotrophoblast cells from the tertiary villi grow toward the deciduum of the cells and spread across it to form the cytotrophoblastic shell. Villi that are connected to the deciduum basalis and the cytotrophoblastic shell are called ingrained villi. Villi that are from the sides of the stem villi are called branch villi. These branch villi are surrounded by the integral space and will serve as the main sites of exchange between mother and fetus. By the fourth week, fetal blood flow is established. Fully oxygenated blood is transported to the placenta from the fetus via paired umbilical arteries. These arteries send branches into the chorionic villi and divide into capillary networks at the terminal end. Carbon dioxide and waste products are removed from the fetal circulation across the placental membrane to the maternal blood in the intravenous space. Oxygen and nutrients are transported across the placental membrane from the maternal blood to the fetal capillaries. Oxygenated fetal blood travels back through the vein, converging to form a stable umbilical vein that goes to the fetus. Blood returns to the maternal circulation through endometrial veins, forced out by the pressure of incoming arterial blood. maturation.
That's why I marvel at the placenta. Do you see all the engineering in there, and that it's just to develop and to sustain the nutrients. So the marvelous little creature that pops out and we say, wow, but the engineering just in this, to overcome several things. Number one, the big thing is to allow nutrients to the baby during development so that the mom's immune system would not destroy it. Just amazing. I know the video on that was a little bit, or the audio was tough to get, but any quick questions? The reason I bring that up, because remember Pastor was talking about when he went through and did the exposition in Psalm 139, and he said being made to craft, kind of weaving together. We looked at the hemoglobin, we looked at the bulk proteins, and then if you look just at the placenta, all of that, amazing, God just crafting that perfectly. So, let's pray. Father, thank you this morning for internet, that we're able just to look at a couple of these videos and be in even further awe of the marvel of things that you do even before we're born. Unseen, taking place, unappreciated by most of us, and yet we see your handiwork in that. Help us, Lord, to get a bigger picture of you in the working of this universe, especially in the spiritual realm. So thank you for this morning, this opportunity to gather together, and as we go into the time of worship, might this further enhance our appreciation, our reverential awe of you, and might our worship be more acceptable. So guide us in your word, be with the pastor in a special way, we pray in your son's name. Amen.